Chapter 9 is focusing on the nucleus and radioactivity. We're going to be exploring natural radioactivity, and this is a process by which some atoms can emit energy and particles. So matter and energy are emitted, and they can come from the nucleus of unstable isotopes. So that's the key. It needs to be unstable. So remembering back in Chapter 3 what an isotope is, they are atoms of the same element that differ in their mass number. So they differ in mass number because they have a different number of neutrons. So looking at the nuclide symbol below, we have X in the center in white, and what that is where the element symbol goes. So if we're talking about oxygen, for instance, X would become O, because that is the atomic symbol of oxygen. A in red here is the mass number. Now, mass number we can calculate by adding the number of protons and the number of neutrons. Okay? Electrons are not involved in mass number. Also remember that mass number is a whole number. It's different than the atomic masses on the periodic table, because the atomic masses on the periodic table are the average of all the isotopes of that particular element. Okay, so A, mass number, the number of protons and neutrons. Looking at Z in yellow here, that is the atomic number. So the atomic number is equal to the number of protons. And if that number is not given to you in the nuclide symbol, you can figure out what the atomic number is just by looking at the periodic table. So not all isotopes are radioactive. Okay, remember from the previous slide we said they need to be unstable, because when they're unstable, that's when they'll start emitting energy and emitting particles. So what we have here are three nuclide symbols. So these are the three isotopes of hydrogen. You'll notice that that bottom number is the same in all three isotopes. That is because that represents the atomic number. And all hydrogen atoms have one proton. If you change the number of protons, you're going to be changing the identity of that element. What differs is the number up top in the upper left-hand corner. That's the mass number. That's the protons and the neutrons added together. Protium, hydrogen 1 here, is the most stable and most abundant. Okay, so since it's the most stable, that hydrogen 1 is not going to be radioactive, because we need an unstable isotope in order for it to be radioactive. So out of these three isotopes of hydrogen, there's only one that's unstable, and that is the last one, tritium. It's rare, and since it's unstable, it can be radioactive. Radioactivity is the emission of particles or energy. So we're going to look at a few different types. First, we'll explore alpha particles and what that looks like and how to identify it. Then we'll move on to beta particles and how to identify that as well. There's also positrons, and last but not least, gamma rays. So we're going to go through each of these types of natural radiation and explore not only how to identify them, but also how to predict products when these isotopes are emitting radiation. So let's start with alpha particles. So it's often represented by this symbol here. And what an alpha particle is it contains 2 protons and 2 neutrons. Okay, well, if it has 2 protons and 2 neutrons, that means its mass number must be 4, because when we calculate mass number, it's the protons and neutrons that we add together. So since it has a mass of 4, it's often represented with the symbol helium, because helium has 2 protons. So this is an alpha particle. You will sometimes see it neutral, and you will sometimes see it with a +2 charge. These particles are very slow moving due to their large mass. So when we look at the other types of radiation, the masses are going to be much smaller than 4. So this is actually quite a large mass for radioactive particles. So since they're so large, they have a low penetrating power. So beta particles are smaller and faster than alpha particles and have a negative charge. So how can you tell, given a reaction equation, if it's a beta emission? Well, what you're looking at is this symbol here. So what does this symbol mean? Well, with beta decay, we're actually having a neutron being converted into a proton. And in order for this to happen, we're losing an electron. So that's what that symbol is representing, is an electron. So if you look, we have nitrogen on the reactant side. Notice the mass number of 16 and the number of protons 7. So what's happening in beta decay is that one of those neutrons out of these 16 total is going to be converted into a proton. So when we go over to the product side, notice the mass number didn't change because the neutron was converted into a proton, but mass number is just protons plus neutrons. So that's not going to affect the total mass number. What it does affect is the bottom number. Notice on the reactant side we had nitrogen, which has 7 protons, but since we converted a neutron into a proton on the product side, we now have oxygen. So notice we went from 7 up to 8 because we added a proton. How did we add a proton? One of the neutrons were converted into a proton. So since we have 8 protons now on the product side, we're talking about oxygen. In order to convert a neutron into a proton, you're actually losing an electron, and that's what this last portion is representing. So with beta particles, you're looking for the loss of an electron, represented by this E and a -1. And you're also seeing the atomic number increasing from reactant to product side. Since these particles are much smaller and faster, they can be stopped by wood, metal, or several layers of clothing. So now let's look at positrons. So positrons have the same mass as a beta particle, except for they have a positive charge. So that's easy to remember, positron, positive. And they're produced from a proton converting into a neutron. So since we have a proton converting into a neutron, we're going to see the atomic number reduced. So how do you recognize a positron equation? Well, by this symbol here, the emission of a proton. That's what the +1 is standing for, proton. Whereas with beta, we saw a -1 right here because it was losing an electron. Well, let's look at the rest of it. Okay, so we have a mass number on the reactant side of 11. So that's the protons and neutrons added together. We then have 6 protons, meaning we're talking about carbon. So if we're having a proton being converted into a neutron, that means one of these 6 protons is going to change into a neutron, which doesn't affect the mass number, but it does affect the number of protons because we just lost one. So it went from 6 down to 5, so now we're talking about boron. The last type we're going to look at is gamma rays, and for this one we're not going to look at an equation or have to be able to identify it based off of a chemical reaction. What we need to know about gamma rays is that they're highly energetic and they have the most penetrating power of all nuclear radiation, So we need lead or concrete to stop gamma rays. So the most dangerous form that we'll talk about. So here's a summary of the ionizing particles that we just talked about, the alpha, the beta, the positron, and the gamma. So this is summarizing what you need to know concept-wise of these particles. So for the alpha particle, its charge is +2. Its mass, 4, because remember it was that helium with a total mass number of 4. Penetration power is low because they were slow and they're large. For beta particles, so this is loss of an electron, so that's why we're seeing a -1 charge, because we had that electron on the product side, because we had a neutron changing into a proton. The mass is 0. and medium penetration power. For a positron, we're looking at a positive charge, right? Loss of a proton in this one. So we had a proton changing into a neutron for positron emissions. The mass is also 0, so therefore its penetration is also medium. For the gamma rays, we didn't have an actual chemical equation showing that, but the charge is 0, the mass is 0, and it has very high penetrating power. So what you need to be able to do is, if you are given a description of one of these particles, you need to be able to identify which particle. For instance, if I say what particle has the highest penetrating power and a charge and mass of 0, gamma. Okay, if I say loss of an electron, medium penetration power, beta. Okay. Now let's look. So using the table on the previous slide, you need to be able to identify the particles depending upon their charge, mass, and penetrating power. However, you also need to be able to identify what type of emission or decay is happening just by looking at the reaction equation. We're even going to take it a step further, and you're going to be able to predict the products given the type of reaction. So, alpha decay or alpha emission is loss of an alpha particle. So if you see this helium, 2 protons and a mass number of 4, then you can identify it as alpha decay because that is an alpha particle. So looking at this reaction, you might just be given the reactant and told, okay, it's an alpha decay, now predict the products. Well, how do you go about doing that? First off, the fact that you're told it's alpha decay, you know one of the product has to be this alpha particle, helium. Okay, how do you predict the other product? We're going to be using what we know on the definition of mass number. So the numbers need to add up is what I'm saying. So you see this number in green, 238, that is the mass number. Well, we know that 4 of those are helium, so that leaves 234 for my other product. What do I mean by that? Well, all of the mass numbers and the number of protons on the product side, once added together, need to equal the mass number and protons on the reactant side. So if I take this 4 from helium and I add the 234 to it, what I get is 238, which is the total mass number of the reactant. I can do the same thing with the protons. So helium, 2 protons. My other product needs to have 90 so that together, when you add them, they equal the 92 on the reactant side. And on the video, I'll be working through some of these where the products aren't there to show you exactly how we can figure out what the product should be. Now for beta decay, we also need to be able to predict the products and identify the type of reaction. So if I'm given this reaction equation in front of me, how do I know it's beta decay? Loss of an electron. Okay, so this guy here. You see that symbol? Loss of an electron, beta decay. Why are we losing an electron? Remember, a neutron is being converted into a proton. So when that happens, that means the number of protons on these nuclide symbols is going to increase by 1 from the reactant to the product side. So it went from 7 to 8 because one of the neutrons was converted into a proton. So seeing that atomic number increase by 1 on the product side is another key that it is beta decay. And I'll go through how to predict those products on the video as well. Now we're just going to look at some general rules for nuclear stability. So some shortcuts, if you will, on how to identify if a nuclei is going to be stable or not. Because remember, in order for radioactivity or emissions to occur, it needs to be an unstable isotope. So how do you tell if it's unstable just by looking at it? Well, some clues are that nuclei with large numbers of protons, so higher than 84, are generally unstable. So we're looking at those big numbers on the periodic table. We've even talked about some of those as being radioactive. Also, if you see an isotope with even numbers of protons and neutrons, they tend to be more stable. Okay, so even numbers tend to be more stable than odd. All isotopes with more protons than neutrons are unstable. Okay, so you don't want to see the number of protons higher than the number of neutrons. And of course, there's always exceptions to every rule, so hydrogen being that exception. So every other isotope other than hydrogen-1. So no more protons than neutrons, it's going to be an unstable isotope and radioactive. So the last concept we're going to look at is half-life, represented by this T1/2. And what a half-life is, it's the time required for 1/2 of any given amount of material to undergo change. Most often that change is decay. So different isotopes decay at different rates. So depending on the isotope, it might take 5 years for a half-life. Others might be 5 seconds. Okay? Each isotope has its own characteristic half-life, and that's dependent upon the stability. The more stable the isotope, the longer its half-life is going to be. But what's true for all isotopes is that if you have 100% of material, when you go through one half-life, by definition, that's when half of the material has undergone change. So half of 100, that means you're left with 50% after one half-life. If you have a second half-life, you're going to lose half of what was left. So you have 50%. Losing half of that gets you to 25%. If you're talking about a third half-life, you have 25%, half of that would give you 12.5%. So after 3 half-lives, all you will have left of the original material is 12.5%. We'll be looking at some calculations on this in the video as well.